All right, so I'll share screen real quick. All right, can you see my screen? Okay, so today we're gonna start off with D equals RT, which you might have seen in school already and might dislike. So this is basically a formula that means distance is equal to rate times time. So D equals RT, what does this really mean? So let's say Joe is traveling at 60 miles per hour in a car. That's a car. And it's going 60 miles per hour. And let's say Joe travels for 30 miles. Then D equals RT could be used to determine how long this takes. So distance equals rate times time. And let's just plug it in and see what it tells us. So 30 is equal to 60 times time, which means time is half an hour. And this is 30 minutes. So let's just look at this and see if it makes sense. So the rate that he's traveling is 60 miles per hour. So in an hour, Joe would travel 60 miles. And it would just make sense for 30 miles, which is half that time or half that distance, to take half the time. So it's half an hour. All right. So notice how we used the same units the entire time. This is 60 miles per hour. And we used miles and hours the whole time. Like, we got 1/2 of an hour and we couldn't have just looked at that and said it's minutes. So it's really important to make sure you're using the right units. So now we're gonna try some problems with D equals RT. And most problems in the AMC8 aren't just gonna be plugging it in. It's gonna be a bit more. So here's the first problem. It's from an AMC8. Wait, you should ignore the people outside if you can hear them. All right, so I'll just let you read it. All right, let's see. Okay, so Joe is going from home to school. This is Joe, and he's walking to school. So he's going that way. So for the first part, and we also know that he runs 3 times as fast as he walked. And he took 6 minutes to walk halfway to school. And also we know that, okay, people are saying the answer. So let's just do this really quick. So if you took 6 minutes to walk halfway to school, then let's say this is the halfway point. And okay, so in order to walk halfway, the second part should be the same distance. So distance for second half is the same. However, let's look at how the rate changes. So the rate triples. And we know that because of this underlined sentence. So from d equals RT, if distance stays the same and rate triples, then time would logically like be 1/3. So 1/3 of normal time, which is 2 minutes. So the second half of the trip takes 2 minutes, and the answer is 6 plus 2, which is 8 minutes. So this is it for this problem. And let's cover a different problem that's like also pretty common in the AMCA. So let's say Joe is traveling, wait. Okay, let's say Joe walks 6 miles per hour, which is pretty fast. If Joe goes 1 mile per hour faster and takes 6 less minutes to go to school, how far is school? Not is walks. So I'll just let you read the problem. No, we're going to be solving problems about Joe this whole time. Hopefully you can read this. I don't know how hard it is to read. All right, so first, let's look at what we know. So normally, we have 6 miles per hour takes R hours. And notice how we're using hours here, because even though this is in minutes, miles per hour is in hours. So it's just easier for us to use that. Wait, not R. Let's use T for time. Okay, so also, if Joe goes 1 mile per hour faster, that's 7 miles per hour, takes T minus 1 over 10 hours. And make sure you know why this works, because 6 minutes is 1/10 of an hour. So now we can use D equals RT. We know that the two distances during this time are equal, like Jennifer says. So 6T is 7 times T minus 1 over 10. And this is just a linear equation in T, so we solve. Was 7T minus 7 over 10. So we get T equals 7 over 10. And we might be wondering, what are the units? So we notice we use hours here. So this must be hours. And this is 42 minutes. So what does the question ask? How far is school? So that means when Joe walks 6 miles per hour, it takes 42 minutes. And since T equals 7 over 10 hours, we use D equals RT one last time. So distance is 6 times 7 over 10, which is 4.2 miles. And that's it for this problem. So D equals RT, there isn't too much. Yeah, D equals RT, there isn't usually too much. It's usually setting variables and then setting some values equal. And we solve that. Yeah, Joe's still going to school during quarantine. So our next topic is sequences in series. So what are sequences? Sequences are basically just a list of numbers, and they don't necessarily have to follow any rules. So let's just have like 4, 3, 7. These are just random numbers, and this could be a sequence. However, we want to look at sequences that are more interesting. So this is just a random. So now we have an arithmetic sequence. And this is one that's like 5, 9, 13, 17. Yes, Joe walks 4.2 miles to school. So we could see what the pattern is here. We notice that it's plus 4, plus 4, plus 4, and so on. So this is an arithmetic sequence because plus 4 is like addition, which is arithmetic. So also we have a geometric sequence. So this is like 3, 6, 12, 24, 48, dot, dot, dot. And this multiplies by 2 every time. And something else to note that is that this number, which is the common ratio, doesn't necessarily have to be like positive. It can be negative as well. So let's consider 3, negative 6, 12, negative 24, 48, dot, dot, dot. Every time it's multiplying by negative 2. And similarly, this is called the common difference, I think. And also similarly, the common difference doesn't have to be positive. Oh, so another interesting one is Fibonacci. So Fibonacci is 1, 1, 2, 3, 5, 8, 13. And you might be able to notice the pattern. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5, and so on. Yeah, Fibonacci is a sequence. I think. I mean, not really. It's called the Fibonacci numbers, but it's technically a sequence. Oh, sequences slash series. Okay, so in the Fibonacci numbers, a formal way to define it is f1 equals 1, f2 equals 1. For any n is greater than or equal to 2, f of n is equal to fn minus 1 plus fn minus 2. So this seems a little confusing. So what does this mean? This just means the first element of the sequence is 1. The second is 1. And for any sequence later, it's the sum of the previous two. So this is 1 plus 1 equals 2. 1 plus 2 equals 3, and so on. And there are a lot of very interesting properties of the Fibonacci sequence. And we might cover that later if we have time. All right, so the first thing we'll do is, or the next thing we'll do is like series. So a series is a sum of a sequence. So like, let's take the sequence 1, 2, 3, 4, all the way to 100. And let's just add them up. This is commonly told as Gauss's method or Gauss's theorem because there's a story about how Gauss was in like elementary school and the teacher got annoyed, so the teacher told him to add these numbers up, and he did it really quickly. All right, so people are saying stuff in the chat already, so I'll just go over the solution. So we noticed that if we write this out, and in the end, we pair these numbers together. 1 plus 101 is 101. Oh wait, 1 plus 100 is 101. Now 99 plus 2 is also 101. So is 3 plus 98. And so is 4 plus 97. So we notice that every two numbers, if we pair the beginning and the end, it creates 101. So now we must compute how many pairs there are. There are 100 numbers, and each pair has 2. So it's just 50 pairs. And each pair has a sum of 101, which gives us a sum of 50-50. So now we might wonder, like, what's a general formula? So 1 plus 2 plus 3 plus ... all the way to n. Let's compute this. So we can use a similar technique. We can pair this up as 1 plus n plus 2 plus n minus 1 plus ... So this is equal to n plus 1, and this is also n plus 1. So each one of these pairs is n plus 1. But how many pairs are there? Well, the first case, it was easier because it was 100. And 100 is an even number. However, we can simply put 100 n over 2 always. Because even if n is odd, the middle number that doesn't have a pair is equal to this, is equal to n plus 1 over 2. So you can try to convince yourself why odd numbers work as well. But there are n over 2 pairs, and each has some n plus 1. So we just multiply them together, and we get n times n plus 1 over 2. So let's test this for the case before, where it's 1 plus 2 plus all the way to 100. So we get 100 plus 1 over 1 over 2, which is 50-50. So we get the same result pretty quickly. Okay. Now let's look at a general arithmetic sequence and try to sum that up. But, okay, yeah. Let's have first term A and common difference D. So we're going to provide a more like rigorous solution, but by looking at the answer, we're going to find that there's a pretty simple solution as well. So what is this arithmetic sequence? So we have A plus D, A plus 2D, all the way to A plus n minus 1D. And we use n minus 1 because this starts with plus 0D. So there are n total elements. So there are n elements. So let's add this up because that's the sequence. I mean, that's the series. So here we can just pair them up. However, what we can do to make it easier is use the formula we discovered earlier. So we notice there are a lot of n's. We notice there are a lot of a's. So how many a's are there? Well, there's one in each of these. And there are n total elements from this. Therefore, we have an. Now, how many d's are there? Well, so there's 0 in the first one, there's 1 in the second, 2, all the way to n minus 1. So this value is from using our previous formula. This is n minus 1 times n over 2. And let's just simplify this now, because this doesn't look very nice. Where's that? Oh, never. Oh, wait, the next step is to factor n out. And then to see what this actually means, let's try to factor n over 2 out. So we arrive at this formula, but this is pretty hard to memorize. So let's write it in a different way. This is n over 2 times a plus d n minus 1. So why is this easier to memorize? Well, notice that in our sequence above, this is the first term, and this is the last term. So this means an arithmetic series, the sum is equal to n over 2 times first plus last. Or this is usually written as first plus last over 2 times n. And n is the number of elements. And why does this make sense like intuitively? Well, if we take the first element and the last element, add them together and divide by 2, we get the average. So this is the average element. And if you take the average and multiply by how many there are, we get the sum. So this makes sense. And this is the usual formula. All right, so now let's look at a geometric series. And just to refresh our memory, a geometric series is one with a common ratio. So this means something like 5, 10, 20, 40, 80, ... where it multiplies by a certain number every time. So we'll compute the formula for a general sequence AR squared, all the way to AR n minus 1. And notice that this is actually AR0 and this is AR1. And this explains why there's n elements. Oops. And R equals the common ratio. So let's sum this up. So inspired by our arithmetic sequence, we try to pair them. However, there's actually nothing that we can get. Like there's nothing we get from pairing them that's useful at all. So maybe we noticed that we can factor a out. However, we find that this isn't useful as well because, well, this actually is if you know a certain factorization, but that factorization shouldn't be well known for AMC8. Therefore, let's do a little like interesting trick. Let this be S. So what if we multiply S by R and we write it like this? So AR plus AR squared plus AR n minus 1 plus ARN. This value is equal to SR. Bruh. Okay, so we take each element and multiply by R, and we go there, there, etc., up to there. Okay, so what do we do now? We notice that these share a lot of terms. Specifically, all of these terms are all shared. So let's subtract them to get rid of the terms. So SR minus S equals ARN minus A. And we want to solve for S. So we factor S out, and then we get S equals ARN minus A over R minus 1, which is A times that. And this is the usual formula that we can see. Or this is the usual formula that you'll see. And this is used to compute the sum of a geometric series. Okay, that's all we have for this part. So now we're gonna do problems. Okay. Yeah, we're gonna do problems now. We already did this one. Okay, let's do the first one. We want to find 4 plus 9 plus 14 all the way to 69. So we use the formula that we had earlier. Oh, Jennifer has a suggestion that you add 1 to each term. And this would work, but I think it's a bit more tedious than just using it. Than just like using the formula. So we compute how many terms there are. So let's look at the sequence. 4, 9, 14 to 69. Oh, wait, yeah. For counting the numbers, we want to count how many numbers are in the sequence. So we add 1 to get 5, 10, 15, all the way to 70. Now we notice all of them are divisible by 5. So we divide by 5. So we get 1, 2, 3, all the way to 14. So there are 14 elements. So n equals 14. Now, if we remember the formula, it's n times first plus last over 2. And this is 14 times 4 plus 69 over 2. And now we just compute this. 73 just 292. Wait, I know I can't do I can't multiply. And this is 511. I think. Yeah, it's 511. All right, so that's it for this for the first part. I feel like I'm gonna run out of room, so I'll move this there. For the second part, we want to compute 3 plus 6 plus 12 plus 24 all the way to 1536. So we multiply by 2 every time to get the sequence. So how many are there? To see this easily, we write them in this form. So look at the exponents now. It goes 0, 1, 2, all the way to 9. So n equals 10. And now we just have to use the formula. And also r equals 2. And a equals 3. So we have a times rn minus 1 divided by r minus 1. And this is 3 times 2 to the 10 minus 1 over 2 minus 1, which is 3 times 1023. So it's 3069. All right, so this is it for question 2. And let's make it small again. So let's do 3. So for this one, it's not very clear what we should do. So let's do some small cases. And this technique is often called engineer's induction, where we test small cases. And it's also a really useful thing to do. So Fibonacci is, let's just write out some terms. So I think that's enough. So let's compute the sum of the first n terms, where n is just a small number. So if n equals 1, then it's 1. If it's 2, then it's 1 plus 1 equals 2. And we don't see a pattern yet, so we continue. 1 plus 1 plus 2 plus 3 is 7. Is 12. And then 1 plus 1 plus 2 plus is 20. So let's look at these numbers now. 1, 2, 4, 7, 12, 20. So if even most of you probably haven't noticed it yet, so let's add 1 to each number to see what happens. So we get 2, 3, 5, 8, 13, 21. And this is identical to this. So there's something with like f of n minus 1. And just by looking at the cases, we guess that 1 plus 2 plus 3 plus, wait, no. We can guess that this holds. But why is this actually true? So to prove this, we're gonna look at, wait, why is this true? Oh, okay. Yeah, I remember. So let's look at this. Let's look at that right there. And let's try to prove it. So we first subtract Fn from both sides. And what is this equal to? So fn plus 1 minus fn, just by the definition of Fibonacci, this is fn plus 1 minus 1. And we repeat, we subtract fn minus 1 from both sides. And we just keep on getting that this number is 2 less than this number. So we continue. And we continue until we get like f1 is equal to f3 minus 1. And this is true because f1 equals 1, f3 equals 2. So this is, that was a check. This is correct. So now we look at this like, I guess, formula or this equation that we got here. So, and let's look at the problem. So we want to compute this, f1 plus f2 plus f3, all the way to f100 in terms of f100 and f101. So we can write f1 plus f2 plus f3. It's equal to f of 102 minus 1. And we want to write it in terms of f100 and f101. So what we have to do is we use the formula, or we use the definition. Wait, do you guys hear the people outside? Oh, you can just ignore them. So yeah, this is our answer. I don't really know what's going on. I think it's just a kid walking by. So this is the next problem. And this problem, like if you've seen it before, it isn't difficult. But if you haven't seen it before, it's very difficult. So I'll just let you think about it for a bit. Unfortunately, it's not C. All right, okay, that's enough time. There's, what are the options? There are no options. Okay, so let's just make this S. Or let's call this S. So what if we square X? Wait, actually, no, we don't have to square X. Let's look at this number inside here. We notice that this number is equal to X as well, or is equal to S as well. So what can we write? S equals the square root of 2 plus S. So now we can square both sides. S squared is 2 plus S. So we get S squared minus S minus 2 equals 0. So this is a quadratic. And also, can you just answer in the chat if you've learned quadratics before? Because we're not sure if we have to cover that next week. Okay. Yeah, it's fine if you don't. So here we can notice that the solution, yeah, I don't think you learned it in school yet. You should learn them in school like 7th grade. I'm not sure. Yeah, so basically the idea here, oh, you learned it in 5th grade? Okay, I didn't know that. Oh, okay. So you can factor this, and we're gonna go over this later, like next class. So don't be worried if you don't understand this. But basically we get s equals 2 or -1. But like -1 is just absurd. So it's not possible for it to be -1. So the answer is 2. Oh yeah, you might have learned it at AOPS. That makes sense. All right. This is also a classic that's like hard if you've seen it before and not hard if you haven't.
Wait, are those plus signs or are those multiplying signs?
These are plus and these are multiply. These are all fractions. Oh, I might have spoken wrong. This is hard if you have not seen it before. Yeah, so nothing cancels at first, but the key idea is noticing, let's compute 1 over n minus 1 over n plus 1. So we have a common denominator and we just subtract. And we notice this is 1 over n plus 1, which is the form that all of these fractions take. So we can rewrite this now. The first fraction, 1 over 1 times 2, is 1 over 1 minus 1 over 2. And 1 over 2 times 3 is 1 over 2 times 1 over 3. Similarly, we can just go on. And let's try replacing this in the original expression here. So this is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. Okay. So that's the final term. And we notice that the negative 1/2 and 1/2 cancel. So do the 1/3, and so on. So this expression is equal to 1 over 1 minus 1 over 101, which is 100 over 101. And this is a pretty nice equation, or this is a pretty nice trick that you might see in like math counts, because math counts likes to do those kinds of things. All right, so let's go to the next problem. Oh, I'm not sure if I'll be able to solve this, but okay. So first, let's notice the pattern here. Let's look at the numerators. This is 1, 2, 3, 5, 8, 13. This is Fibonacci. And the denominators, 2 is 1 times 2. 3 is 1 times 3. 10 is 2 times 5. Yeah, this is a pretty confusing problem. 3 times 8. And where are these numbers found? In Fibonacci, there's 1 in the beginning. So it multiplies those two, then those two, then those two, then those two, and so on. And we don't want to just compute this. So, all right, so this is just like the pattern that this series takes. I mean, I guess it's kind of like shoelace, but not really. All right, so each element in this series, since we don't want to compute this like just by hand, each element, so we notice that the numerator is, let's say, Fibonacci I. Then let's look at this. So 24 is 3 times 8, which are these two numbers. So each one is f I minus 1 times f I plus 1. So now we sum this number up. So I'll let you guys think about it for a bit. And a hint to this problem is like the previous one. So maybe you could subtract two fractions and create this one. All right, whatever. So I'll just give the solution now. So this is really similar to the last problem. So let's consider f 1 over f I minus 1 minus 1 over f I plus 1. Just by giving a common denominator, this is f I plus 1 minus f I minus 1 over f I minus 1 times f I plus 1. So how do we simplify the numerator? And to simplify it, let's use the definition of Fibonacci. So by the definition, fi plus 1 is equal to fi minus 1 plus fi. This is just the definition. So if we manipulate this equation, f of I plus 1 minus f of I minus 1 is f of I, fi. So this is equal to fi over fi minus 1. And we notice that these two are equal. So that means that this equation is indeed correct. So how do we plug this back in? Well, so 1/2 is equal to 1 over f0 minus 1 over f2. And we can actually confirm this. This is 1 over 1 minus 1 over 2 is 1/2. The next element, which is 2/3, is 1 over f1 minus 1 over f3, which is 1 over 1 minus 1/3. And so on. We can continue writing this until 13 over 168 is 1 over f, I think the 1 over f5 minus 1 over f7. So when we add all these numbers up, a lot of stuff cancels, just like the last one. Also, this problem is really like not standard, and you're probably not gonna see it on like AMCs or like math counts, and it's just like a cool idea. And everything here cancels except for those terms. And the rest is just computation. Let's write this out one more time. So this is 13. This is 21. So this is just 1 over 1 plus 1 over 1 minus 1 over 13. So we compute this, and this is just equal to a big number. Fibonacci, I think you can just search it up, and there are like there's stuff about it. But I don't know if there's a specific chapter in AOPS books that have Fibonacci. So lastly, I'm gonna give like, I guess it's more of a puzzle than a math question. Actually, it's kind of a math question. So we have two trains. They're going towards each other at 40 miles per hour. And people weren't being smart. So that means they're on the same track. Yeah, what could go wrong? So now there's a bird. How do you draw a bird? That's a bird. The bird is flying between the two trains. So basically the bird starts here, flies over here until it meets this train, then flies back until it meets this train, and keeps on going like that. Let's say this distance is 200 miles. How far does the bird travel? So my solution to this at first was very not smart. And it involved like calculating all of these times and then summing a geometric series. But there's a lot smarter way. So I'll let you guys think about it for a bit. Basically until the end of class. Until I'll give a solution real quick. Oh, how fast is the bird? Let's say 20 miles per hour. Yeah, it's 200 miles between the trains. Oh, and this should be the distance between the two starts, if that makes sense. $200 miles. Everything's in miles or miles per hour here. Yes, there's 5 minutes left. So I have to stall like 3 more minutes. The bird starts on this train right here. Wait, Justin, what was your answer? 100 miles? Oh, wait, the question, I didn't even ask the question. How far does the bird travel? Let me compute the answer real quick. I don't remember it.
So every time the bird like flies to the other train, how much closer do they get?
That's something that you'll have to compute. Or like you don't actually have to compute it. Also, Andrew got it right, I think. No, the bird is like a super bird. Oh, wait, that's a good point. The bird falls behind. Let's say it's 80 miles per hour. Sorry, yeah. The bird falls behind. All right, I think I'll just give a solution and like let you guys out early. So basically, the bird is traveling 80 miles per hour the entire time. So what does this mean? There's a constant speed that it's traveling. And all we have to do is compute the time that it travels for. And how long is this? The trains are essentially moving at 80 miles per hour. Well, like they're actually moving 40 miles per hour each, but relative to each other, they're moving 80 miles per hour. And distance is 200, rate is 80. And this means time is 2.5 hours. And this means the bird is traveling for 2.5 hours. So D equals RT, and we get the the distance traveled is 200 miles. And that's the answer. Oh, according to Charlie, this was a Math Counts Nationals team number 10, which is like probably the hardest problem in Math Counts. And it was in his physics homework, which is how I got introduced to it. All right, it's 6. You can go. Bye.